Envision standing before an unexplored doorway. Behind it lies something that defies physical laws, absorbs light, and conceals universal mysteries within itself. What occurs inside a black hole? Where does matter disappear after crossing the event horizon? Could it become a gateway to another reality? Or does something even more incredible hide within? A new universe. In this video, we'll embark on a scientific investigation to solve one of cosmos' greatest enigmas. Armed with relativity theory, quantum mechanics, and the boldest hypotheses, we'll peer into places where known physics ends. To ensure you don't miss the most fascinating content, subscribe to our channel, hit the notification bell, and together we'll unravel universal secrets. What constitutes a black hole? Picture yourself strolling along a beach when suddenly you spot an enormous whirlpool in the sand. It draws everything nearby inside. Small pebbles, shell fragments, even your flip-flops. You attempt to look inside, but only darkness exists. Well then, a black hole resembles such a whirlpool, but in space. Instead of sand, it pulls in stars, planets, light, and even space-time itself. A black hole represents a location in the universe where gravity becomes so powerful that nothing can escape outward, not even light. If you fall into one, that's it. You've vanished forever. But here's the trick. A black hole isn't actually hollow. It's not a hole in reality's fabric, but rather an ultradense object so heavy that even surrounding space curves around it. How do black holes form? Imagine constructing a sand castle. It's beautiful and tall, but at some point the sand begins collapsing under its own weight. If nothing stops it, it simply crumbles into a dense lump. Now picture a star, not just a glowing in the sky, but a nuclear reactor the size of 1,000,000 Earths. Inside it, atoms constantly explode, creating colossal outward pressure. Gravity tries to compress it, but thermonuclear reactions resist, and so the star lives for millions of years. But then fuel runs out. Reactions fade, and now gravity takes control. Imagine having a huge balloon and suddenly releasing all the air. It deflates, but doesn't simply fall. It collapses to insane dimensions. Gravitational collapse. When a star 20 times heavier than the sun lives out its lifespan, it engages in a final battle with gravity. Its outer layers explode as a supernova, scattering matter millions of kilometers around. But the core begins contracting. Pressure becomes so intense that atoms break apart. Electrons get pressed into protons, transforming into neutrons. If the star were slightly lighter, it would become a neutron star, an object city-sized but with the sun's mass. But if there's too much mass, nothing can stop the collapse. Matter collapses into a point. Gravity becomes infinite. Space curves so extremely that even light cannot escape. Around this point forms an event horizon, an invisible boundary beyond which nothing can break free. Imagine walking on a beach and suddenly finding yourself in quicksand. You struggle, but the more you thrash, the deeper you sink. Only with black holes, there's no rescue at all. If you've crossed the event horizon, that's it. There's no way back. Even if you could accelerate faster than light speed, you still wouldn't escape. This is how black holes appear, monsters devouring space and time that nobody has seen, but everyone fears. Event horizon, the point of no return. Picture floating down a river and suddenly seeing a waterfall ahead. The closer you get, the stronger the current becomes. At some moment comes the point of no return, a boundary after which even the most powerful motor won't save you. You're doomed to fall down. This is the event horizon. A black hole is a bottomless cosmic funnel, and its event horizon is that very edge beyond which begins a one-way ticket. Once you cross it, that's it. There's no way back. At all. Even if you had a hypothetical engine that could accelerate faster than light speed, which is impossible, you still wouldn't escape. How does this look from outside? Suppose your friend flies in a ship directly into a black hole, and you observe this from aside. Initially, everything's normal. He waves at you, transmits an okay signal, and even jokes about the most extreme vacation. But then he approaches the event horizon and begins slowing down. The closer he gets, the slower he moves. At some point, he freezes in place. It seems to you that he's stuck on the black hole's edge. His light dims, turning into a red spot, then disappears completely. But this is an illusion. Actually, for him, time flows normally. He long ago crossed the boundary and races into the depths. It's just that gravity is so strong that even light from him can barely escape. What does someone already inside feel? Now imagine that you're crossing the event horizon. For you, this looks ordinary. No flashes, no warning signals. Space around distorts, but physics laws still work for now. You continue falling into darkness. But here's the problem. Time and space begin going crazy. Depending on the black hole size, there are two scenarios. If the black hole is small, you get violently torn apart into atoms. This process is called spaghettification. The gravity difference between your head and feet becomes so enormous that you stretch out into a long thread like pasta. If the hole is large, for example, supermassive at a galaxy's center, you pass through the event horizon completely painlessly. You might not even immediately realize that anything has changed. But here's the trouble. After some time, you still face the singularity point where gravity is infinite. What's there in the center, nobody knows. Perhaps you get compressed to a state of zero. Perhaps you fall through into another universe. But one thing's certain, there's no way back. Singularity, a place where physics laws break down. Imagine you're on a huge trampoline. If you place a tennis ball on it, it bends slightly. If you put something heavier, say, a weight, the depression becomes deeper. Now visualize placing something infinitely heavy on the trampoline. But here's the problem. The trampoline simply tears. The same thing happens in a black hole center. There, where matter compresses into a point of infinite density, space and time break down. This is the singularity. What's inside there? Scientists have no idea. Classical physics says it's a point of infinitely small dimensions with infinitely large mass. But physics doesn't like infinities. This means our equations simply stop working. Some theories suggest that in a black hole center, all matter compresses into something like a one-dimensional line. Others say these are portals to other parts of the universe. Maybe it's an exit to a parallel reality. But most intriguing, there's a hypothesis that inside black holes, new universes might be born. Imagine that the Big Bang occurred inside one of these singularities. Perhaps our universe is simply one of many that appeared in black holes of other, older universes. Why don't we know for certain? It's simple. Nothing that enters a black hole can escape from there. No signal, no information. It's like a sealed box that can't be opened. The only way to learn what's inside is to go there yourself. But that would be a one-way ticket. Do black holes evaporate? Hawking's theory of black hole radiation. Imagine you have a huge iceberg. It looks monolithic and eternal, but if you look closely, drop by drop, molecule by molecule, it still loses its mass and evaporates. Black holes, strangely enough, behave similarly. Paradox. A black hole isn't so black after all. For a long time, it was believed that black holes are absolute vacuum cleaners. Everything that falls into them never returns. But Stephen Hawking in 1974 proved this isn't entirely so. A black hole doesn't just devour matter, but also slowly loses mass itself, emitting so-called Hawking radiation. This is a process where, due to quantum effects at the event horizon boundary, particle pairs are born. One particle falls inside, while the other goes into space, taking with it part of the black hole's energy. How does this work? Vacuum isn't emptiness, but seething chaos. Virtual particles constantly appear and disappear in it. Usually they annihilate, but at the event horizon, everything's different. If one particle goes into the hole while the second flies outward, this means the black hole has lost part of its energy, and according to Einstein, energy and mass are connected. So losing energy, the black hole also loses mass. What happens in the end? If a black hole loses mass, then sometime it will disappear. But this takes astronomically long periods. For black holes the size of the Sun, this process lasts longer than the universe's age. But if we're talking about tiny black holes, they evaporate faster and eventually disappear with a powerful energy burst. This means a black hole isn't an eternal prison, but a temporary formation, albeit incredibly long-lasting. In some sense, even they aren't eternal. Information paradox. What happens to information absorbed by a black hole? Imagine you have a hard drive with billions of terabytes of data. You accidentally drop it into lava. The disk burns up. But in theory, all information recorded on it simply redistributes as heat, smoke, and ash. Now imagine this disk falls into a black hole. And here the problem begins. Why is this a paradox? According to quantum mechanics laws, information in nature doesn't disappear. Even if an object burns or gets torn apart into atoms, theoretically its initial state can be restored. But when something crosses a black hole's event horizon, it disappears without a trace. No information about it remains outside. Stephen Hawking in 1974 discovered that black holes aren't eternal. They evaporate due to quantum effects emitting so-called Hawking radiation. The problem is that this radiation is random and carries no information about what was absorbed. If a black hole completely evaporates, all information it sucked in disappears. But this is impossible from quantum physics standpoint, hence the paradox. Possible solutions. First, the holographic principle. Physicists suggested that information gets recorded on the event horizon as a hologram. This relates to string theory, according to which our three-dimensional universe might be a projection of information recorded on a two-dimensional surface. Second, information exits with Hawking radiation. If black hole radiation isn't random but contains encoded data, then all information about absorbed objects could theoretically return to the world. But we don't yet have technology to verify this. Third, wormholes and parallel universes. Some scientists think information doesn't disappear, but simply transfers to another dimension or universe through wormholes inside black holes. But so far this is pure hypothesis without experimental proof. Why is this important? The information paradox is key to unifying quantum mechanics and general relativity. If we understand what happens to information in black holes, this could lead to discovering new physics and understanding how the universe works at the most fundamental level. Black holes are places where classical physics breaks down and quantum mechanics begins creating havoc. Imagine taking all nature's laws, twisting them into a dense ball, and stuffing them into a black hole. What results? Chaos. But quantum mechanics might help sort out this madness. Why general relativity can't cope. Einstein described how mass curves spacetime. The more massive an object, the stronger its gravity. But in a black hole center at the singularity, density becomes infinite. General relativity equations simply explode. Imagine dividing a number by 0. Mathematics says error. Physics also says error. So we need another theory. Quantum mechanics and black holes. Quantum mechanics describes the microworld of particles and probabilities. In this world, energy isn't infinite and emptiness isn't empty. Vacuum seeds with virtual particles that appear and disappear. Hawking realized that at the event horizon, these particles can separate. One falls inside, another flies outward. Thus the black hole slowly evaporates. But what's inside? Theories about what hides in black holes. First, quantum foam. If we look inside a black hole, we might see not an infinitely dense point, but chaotic quantum warfare. Space-time inside might bubble and fluctuate at Planck scales, turning the black hole's center into something completely unpredictable. Second, wormholes. Some physicists think that instead of destroying space, a black hole's interior connects with another part of the universe or even another universe. Imagine a black hole isn't a dead end, but a portal. Einstein-Rosen theory describes how wormholes might arise, but nobody has observed them yet. Third, quantum gravity saves physics laws. If quantum mechanics and gravity are combined, perhaps we'll get a new theory explaining what happens inside. Currently, there are different approaches: loop quantum gravity, string theory, holographic principle. But until we have a unified quantum gravity theory, this remains a mystery. Why is this important? If we understand how matter behaves inside black holes, we can understand how the universe arose. Singularity in black holes resembles what existed at the Big Bang moment. Perhaps black holes are the key to understanding reality's very existence. Black holes and relativity theory. Why did Einstein change our understanding of spacetime? Imagine driving on a perfectly smooth road. Everything's clear and predictable. This is how scientists thought before Einstein. They considered space and time simply background against which events occur. But Einstein turned everything upside down. He proved that space and time aren't static but can stretch, compress, and even twist. And most importantly, mass affects them. The more massive an object, the stronger it curves surrounding space-time. Imagine placing a tennis ball on a trampoline. It bends slightly. If you put a cannonball, the trampoline sags much deeper. In space, this means stars and planets curve space around themselves, forcing objects to move along curved trajectories. But what if you take something so massive that it curves space-time to the limit? Then a black hole appears. Relativity theory predicted that if a star is massive enough, after its death it can compress into a point of infinite density, a singularity. Around it forms an event horizon, a boundary beyond which gravity becomes so strong that even light can't escape. What does this mean practically? If you flew toward a black hole, outside observers would see your movements slow down. For you, time flows normally, but approaching the event horizon, you'd see strange things. Light would become redder, space would seem stretched, and time might lose meaning entirely. Einstein changed our understanding of the universe. He showed that gravity isn't just a force, but a manifestation of space-time curvature. Black holes became the most extreme proof of his ideas. Wormholes, myth or reality? Are black holes connected to hypothetical spatial tunnels? Imagine needing to get from one end of a city to another. Usually you drive through streets, turn at intersections, and sit in traffic. But what if a secret tunnel existed that instantly transports you directly to the needed place? This is the wormhole idea. A wormhole is a hypothetical space-time tunnel connecting two distant points in the universe. The concept appeared in 1916 when Ludwig Flamm, studying Einstein's general relativity equations, noticed that bridges between two space regions might exist. In 1935, Einstein and Rosen developed this idea, calling such constructions Einstein-Rosen bridges. But are they connected to black holes? In theory, yes. Mathematically, equations describing black holes allow for tunnels leading to other parts of the universe or even other universes. But there are problems. First, stability. Ordinary black holes destroy everything entering them. So traveling through them is, mildly speaking, not the best idea. For a wormhole not to collapse, exotic matter with negative energy is needed to support its structure. Such matter is theoretically possible, but hasn't been discovered yet. Second, size. Even if wormholes exist, they might be microscopic, making them useless for travel. Third, radiation. Even assuming someone could create a stable wormhole, destructive energy might accumulate in it due to quantum effects, leading to instant collapse. Bottom line, on paper, wormholes are possible and physics laws don't forbid them. But practically none have been found, and even if they exist, using them for travel isn't currently feasible. So for now, this is closer to science fiction than reality. Can a black hole be a portal to another universe? Hypothesis of multidimensional realities. Imagine a black hole isn't just a bottomless pit, but a door leading somewhere beyond our understanding. Sounds like fantasy, but some physicists actually think black holes might be portals to other universes. This idea emerged from Einstein's general relativity. His equations allow for white holes, hypothetical objects behaving opposite to black holes. If black holes suck everything inside, white holes eject matter outward. Some scientists suggest that black holes in our universe might be entrances, while white holes are exits in another reality. Another version relates to the multidimensional universe hypothesis. According to string theory, our universe might be just one of infinite worlds existing in higher dimensions. If so, black holes might be tunnels between these worlds. But there's a problem. What happens to information falling inside? According to standard physics, everything crossing the event horizon inevitably falls into singularity, a point of infinite density where physics laws stop working. But quantum mechanics suggests information can't simply disappear. If it's somehow preserved, perhaps it's not destroyed but rewritten in another reality. However, verifying this is currently impossible. Even if a black hole is a portal, nobody could return and tell about it. Besides, the journey through it would hardly be pleasant. Gravity would tear anyone apart into atoms long before the transition. So for now, the idea of black holes as portals remains an interesting hypothesis, but without proof. Perhaps future quantum gravity and new technologies will let us learn more. But for now, this is still closer to science fiction than reality. What lies beyond the event horizon? If you cross a black hole's event horizon, there's no way back. No brakes, no life preservers. This is the point of no return after which even light can't escape. But what next? First scenario, classical. You fall inside and approach the singularity, a point of infinite density. Gravity stretches you like spaghetti because your feet, if you're falling feet first, are attracted more strongly than your head. This effect is called spaghettification. By the time you reach the center, you've become a stream of elementary particles. But there's another option. If space and time switch places inside a black hole, approaching the singularity becomes inevitable, like moving forward in time. But some theories, like loop quantum gravity, suggest the singularity might not exist in the usual sense. Perhaps inside a black hole, space doesn't collapse but leads to another universe region or even another universe. Another hypothesis, black holes' internal structure might be like a tunnel. In this case, if you fall into the right black hole, there's a chance you won't be torn apart, but will enter a white hole, a hypothetical object that would eject you into another corner of space, or a completely different reality. This is pure theory, but it's based on solutions to Einstein's equations. But there's a problem. Quantum mechanics requires that information doesn't disappear. If you fall into a black hole and disintegrate, what happens to your information? One option is that information gets recorded on the event horizon surface as a hologram and eventually evaporates with the black hole itself due to Hawking radiation. So, if you fall into a black hole, you'll most likely die. But what happens to your information? And there's just a chance that something greater hides inside black holes. This is a question modern physics doesn't yet have a precise answer to. Black holes and the Big Bang. Could our universe be born from a black hole? There's a hypothesis that our universe could have been born from a black hole. Sounds wild, but let's figure it out. Let's start with the fact that a black hole is an object with infinite density and gravity from which even light can't escape. At its center is a singularity, a point where classical physics simply breaks down. Now, let's remember the Big Bang. The universe's beginning is also described as a singularity where all matter and energy were compressed into one point, then suddenly scattered in all directions. Now imagine that each black hole in our universe isn't an end, but a beginning. What if inside each black hole a new universe is born, and its event horizon is simply a boundary we can't see beyond? This idea was promoted by physicist Lee Smolin. His theory is called cosmological natural selection. He suggested that universes are born through black holes and evolve like living organisms. Universes that produce more black holes create more children and thus live longer. There's also the idea that the Big Bang could have been a white hole. A white hole is a hypothetical object, the opposite of a black hole. If a black hole only absorbs matter, a white hole conversely ejects it outward. What if the Big Bang was just such an ejection from another universe's black hole? The problem is we have no way to test these hypotheses. We can't look beyond a black hole's event horizon, and we don't know what existed before the Big Bang. But the connection between them is too obvious to ignore. Perhaps our universe really was born from a black hole, and perhaps in distant corners of space, inside black holes, new universes are being born right now. Do white holes exist? Hypothesis of reverse black holes ejecting matter. White holes are theoretical objects behaving opposite to black holes. If black holes suck in matter and don't release it, white holes conversely only eject substance and don't allow anything to penetrate inside. The white hole idea appeared as a solution to Einstein's equations. Black holes are described by general relativity. If you simply mathematically reverse time backward, you get an object that instead of absorbing matter ejects it. But here problems begin. Black holes exist. We observe them. But white holes don't. If a white hole appeared in the universe, it would be incredibly unstable. Any atom, even a light photon trying to approach it, would cause its instant destruction. It's like trying to launch a reverse explosion, but the slightest external touch would disrupt the whole process. One of the craziest hypotheses suggests our Big Bang is a white hole. In this scenario, our universe appeared as matter ejection from a singularity that was a black hole in another universe. If this is true, then white holes exist, but they can't be observed directly because they create new realities. Another hypothesis relates to quantum mechanics. In loop quantum gravity theory, black holes might transform into white holes when they reach their density limit. If a black hole doesn't completely evaporate due to Hawking radiation, at some point it might collapse and become a white hole, ejecting back all absorbed matter. But so far this is all pure theory. We have no proof of white holes' existence. But if we ever discover an object that suddenly ejects huge amounts of matter without apparent reason, this might be the first hint of their reality. Dark matter and black holes. Is there a connection between invisible matter and black holes? Dark matter is one of the most mysterious things in the universe. We know it exists because it gravitationally interacts with ordinary matter, but it's invisible, doesn't emit light, doesn't reflect it, and doesn't even absorb it. It's literally space's ghost. Now black holes, objects possessing such strong gravity that even light can't escape. The coincidence seems obvious. Maybe dark matter is black holes, or at least somehow connected to them. There's a hypothesis that dark matter consists of primordial black holes that could have formed right after the Big Bang, not as a result of stellar death. If there really were many of them, they could explain the strange gravitational effects we attribute to dark matter. But there's a problem. If dark matter were black holes, we'd notice microlensing effects, when a black hole passes in front of a distant star and temporarily amplifies its light like a lens. We've conducted such experiments and didn't find enough events to explain all dark matter. Another theory says black holes might attract and concentrate dark matter. Since dark matter doesn't interact with ordinary substance, it can accumulate around black holes, forming a kind of dark corona. If so, black holes might be key to solving dark matter's nature. The boldest hypothesis is that dark matter and black holes might be connected through quantum physics. Some scientists think dark matter is a kind of holographic manifestation of information stored on black holes' event horizons. If this theory is correct, then there's not just a connection between them. Dark matter might be a side effect of black holes' existence. We don't have a precise answer yet. But if a connection exists, studying black holes might become key to understanding the universe's most mysterious substance. Black holes and time travel. Can they help move to the past or future? If you want to time travel, black holes are one of the most intriguing options. They're so powerful they curve space-time, theoretically allowing glimpses into the future or even returns to the past. Let's figure out how realistic this is. Let's start with Einstein's general relativity predicting that strong gravity slows time. This means if you're near a black hole, time will flow slower for you than for everyone else. For example, if you spend a year near a supermassive black hole like an interstellar, decades or even centuries might pass on Earth. Technically, this is already time travel to the future. But what about the past? Here, everything's more complex. There's a hypothesis that rotating black holes, so-called Kerr black holes, might contain wormholes inside, tunnels to other places in time or space. If such a black hole really had a stable wormhole, you could enter it and exit at another universe point or even another time moment. The problem is such tunnels are most likely unstable. The slightest disturbances and the wormhole collapses faster than you can say, "I'm in the future." Physicists like Kip Thorne proposed using exotic matter with negative energy to stabilize such tunnels. But so far this is pure theory. Another idea is time loops, or so-called closed time-like curves that might arise in a black hole's curved spacetime. They theoretically allow movement to the past, but their existence contradicts many fundamental physics principles, including causality. In other words, if such loops exist, you could kill your own grandfather and create a paradox. Physics laws don't really like such things. Generally, black holes really might be time machines, but only toward the future. Travel to the past, if possible, would require something more than just jumping into a black hole. For example, fundamental revision of physics laws. Black star hypothesis. Could a black hole be something other than commonly believed? When we say black hole, most imagine a bottomless cosmic maw devouring everything around. But there's a hypothesis that black holes aren't quite holes. Maybe they're not holes at all. Meet the black star concept. An ordinary black hole, according to classical physics, is an object with such powerful gravitational field that even light can't leave it. But here's what's strange. Einstein's general relativity perfectly predicts black holes' appearance, but inside them should be a singularity, a point with infinite density where all known physics laws break down. Sounds like we're missing something. Alternative theory suggests instead of a black hole, a black star. This isn't quite a star because there's no nuclear burning, but it's not quite a hole either. The idea is that inside a black hole might be not a singularity, but something else. For example, ultradense matter held by unknown quantum effects or even dark energy. There's a version that black stars form the same way as ordinary black holes, but just before collapse, some unknown physics appears that prevents singularity formation. For example, quantum gravity or exotic fields create pressure preventing matter from completely collapsing. The result is an object that looks like a black hole from outside, but inside, instead of an infinitely dense point, there's something else. Some scientists even suggest black stars might emit radiation similar to Hawking radiation, but for other reasons. If true, then someday it might be possible to distinguish them from classical black holes simply by measuring how they lose mass. So perhaps we still don't understand what black holes really are. Maybe they're not doors to nothingness, but some exotic objects operating by physics laws we have yet to discover. How do black holes affect galaxies? Their role in universal evolution. If you think black holes are just gravitational vacuum cleaners sucking up everything, you're underestimating their influence. Actually, black holes are cosmic orchestra conductors. Without them, galaxies might look completely different or might not exist at all. Let's start with galaxy centers. Almost every large galaxy has a supermassive black hole sitting inside. For example, at our Milky Way's center sits Sagittarius A*, a monster with about 4 million solar masses. This thing doesn't just mindlessly absorb matter, it actively participates in the entire galaxy's formation and evolution. First, there's a process called active galactic nucleus. When matter falls into a black hole, it accelerates, heats to frenzied temperatures, and begins radiating gigantic amounts of energy. In especially active black holes, quasars form, some of the universe's brightest objects. Their power can exceed the entire galaxy's luminosity by thousands of times. This process affects star formation. If a black hole ejects enough energy and radiation, this can heat galaxy gas, preventing it from compressing into new stars. But if energy streams are directed differently, they might conversely compress gas clouds and stimulate new star birth. So black holes can both kill star formation and encourage it. Second, black holes create powerful relativistic jets, plasma streams ejected from poles at near-light speed. These jets can pierce entire galaxies and even escape beyond their boundaries, affecting intergalactic medium. They can blow gas away, hindering star formation, or conversely mix matter, creating favorable conditions for new stellar generations. Another important point is black holes' influence on galaxy mergers. When two galaxies collide, their central black holes begin approaching, swirling gigantic gas masses and causing star formation bursts. Eventually, these black holes might merge, releasing colossal gravitational waves we've already learned to detect with laser interferometers like LIGO. So black holes don't just sit in galaxy centers. They regulate their growth, control star formation processes, and can even determine how active a galaxy will be in the future. Without them, the universe would look completely different, and perhaps our own galaxy would never have formed as we know it. Primordial black holes. Possibility of mini black holes existing since the early universe. When we talk about black holes, we usually imagine giants like Sagittarius A** at the Milky Way center, or even more massive objects in distant galaxies. But what if black holes exist the size of asteroids or even elementary particles? Such objects are called primordial black holes, and if they exist, they might be flying through you right now. The primordial black hole idea appeared in the 1970s. Famous physicist Stephen Hawking proposed it. The essence is that in the first moments after the Big Bang, the universe was so dense and chaotic that in some regions, areas with extreme energy concentration could arise. If such areas became dense enough, they collapsed into black holes. The main difference between primordial and ordinary black holes is they don't form from stellar collapse. Their mass could vary widely, from microscopic sizes to hundreds of solar masses. The smallest would evaporate due to Hawking radiation, turning into pure energy. If such mini black holes existed, today their final flashes could be detected as gamma-ray bursts. But if some were massive enough to survive billions of years, they might still exist. Some scientists suggest such objects might constitute part of dark matter. Nobody sees dark matter, but it must exist to explain galaxy movement. Primordial black holes perfectly fit this scenario because they're small, invisible, and interact with ordinary matter only through gravity. But how to find them? One way is searching for gravitational lenses. If a small black hole flies in front of a star, it bends light, making the star flicker. Such effects have been observed, but so far there's no proof of primordial black holes' existence. Another hypothesis relates to the Antarctic Neutrino Telescope ice cube. Several years ago, it detected strange events, powerful particles seemingly flying from underground. Some scientists suggest these might have been primordial black holes passing through Earth. If primordial black holes exist, this could revolutionize our understanding of the universe. Perhaps they're hiding in dark matter, or maybe billions of mini black holes are permeating our planet right now, and we don't even notice. Consequences of falling into a black hole. Imagine you're flying in open space, and there's a black hole before you, enormous, dark, with a bright accretion disk around. What happens if you approach too close and cross the event horizon? Initially, nothing special. You're freely falling, not feeling acceleration like astronauts in orbit. But the closer to the black hole, the stronger gravity becomes. If you're falling feet first, attraction in the foot area becomes stronger than in the head area. Your body begins stretching while pressure squeezes it in the transverse direction. This phenomenon is called spaghettification. But there's a nuance. If the black hole is small, stellar mass for example, spaghettification begins even before the event horizon, and you simply tear apart into atoms. But if you're falling into a supermassive black hole, like what's at a galaxy center, the event horizon will be crossed without noticeable changes. What happens next? Here physics stops being intuitive. For an external observer, you never cross the event horizon. The closer you get, the slower your time flows. To a distant astronaut, you seem to freeze at the boundary while your light becomes increasingly red until it disappears. But for yourself, time flows normally. You cross the event horizon and continue falling. All paths lead only downward. Space around begins spinning like a whirlpool. Where you're dragged next depends on the black hole's mass and properties. If it's an ordinary black hole, a singularity awaits you, a point of infinite density where physics laws stop working. You compress to an infinitely small point and disappear. But if the black hole rotates, the situation changes. Theoretically, it might have regions where gravity doesn't crush you to a point, but allows you to fly out to another space location or even another universe. This is called a wormhole. Another option, if white holes exist, the opposite of black holes, you might fly out of them elsewhere in the universe. But not one white hole has been found yet, so falling into a black hole is a one-way ticket. For an external observer, you disappear. For yourself, you fly into the unknown, and what awaits next, nobody knows. Future black hole research. What experiments will help reveal their secrets? Black holes are physics' most mysterious and extreme area. To understand their nature, scientists need to go beyond conventional science bounds. But how do you study an object that by definition releases no information? The first key is observation of their environment. Black holes aren't visible, but they can be detected by how they distort light and absorb matter. The first event horizon image in history was taken in 2019 using the Event Horizon Telescope, an array of radio telescopes across the planet united into one virtual Earth-sized telescope. In the future, astronomers want to create a space version of this telescope. Without atmosphere interfering with observations, resolution will be 1,000 times higher. It will be possible to see accretion disk details and even verify whether black holes really correspond to general relativity predictions. The second key is gravitational waves. Black holes merge, and at this moment space-time literally vibrates like water surface from a thrown stone. Detectors like LIGO already register such events, but sensitivity is limited. Future detectors like LISA will operate in space and detect even small oscillations, revealing more details about black holes' nature. The third path is studying quantum effects. Hawking's theory predicts that black holes slowly evaporate by radiating energy. But this remains an unverified hypothesis. Perhaps in the future we'll manage to detect this radiation directly or even create miniature black holes in particle accelerators. Such experiments could link quantum mechanics and gravity, currently considered one of physics' main unsolved problems. But the most ambitious idea is sending a probe into a black hole. Theoretically, if we could transmit data from an apparatus approaching the event horizon, this might give us critically important information. But this requires technologies that don't yet exist. Black holes are extreme physics laboratories where familiar reality laws break down. By studying them, we approach understanding the universe's most fundamental mysteries, and perhaps someday we'll discover something that will overturn our entire worldview. So we've peered into space's most frightening and mysterious region. Black holes aren't just dark gravitational traps. They're portals where relativity and quantum mechanics laws collide, where matter disappears and possibly new universes are born. We learned how they form, why they evaporate, and whether they might conceal wormholes. We figured out what happens to information falling beyond the event horizon, and how black holes might be connected to dark matter and even the Big Bang itself. But this is only the iceberg's tip. Scientists still don't know what lies beyond the event horizon, and perhaps exactly here hides the next great physics revolution. If you enjoyed this journey through the universe's most mysterious corners, subscribe to our channel. There will be even more scientific investigations, hypotheses, and theories that blow your mind. And who knows, maybe someday we'll find a way to truly look inside a black hole.